Hello and welcome back to yet another calculus video. Today we have this really cool integral. It's the integral from 0 to pi by 2 of the logarithm of x squared plus the logarithm squared of cosine x dx. Yeah, that is one hell of an integral we're evaluating. Now, how exactly do we approach this? Well, I tried it using Feynman's trick of differentiating under the integral sign, and that worked out pretty nicely. So we'll define an integral function I of some parameter alpha, and we'll define it as the integral from 0 to pi by 2 of the logarithm of x squared plus log squared alpha cosine x. So we've introduced the alpha parameter as part of the argument of the second logarithm function. And this is pretty nice because when we differentiate it, we'll get a very nice structure to work with in the context of some multivariable calculus. So we now plan to differentiate the integral function with respect to the alpha parameter, and switching up the order here gives us the integral from 0 to pi by 2 of the partial derivative with respect to alpha of log x squared plus log squared alpha times cosine x dx. And differentiating, we have this argument of the logarithm in the denominator now. We have x squared plus log squared alpha cosine x, and now we have to differentiate this argument with respect to alpha. So x here is being held as a constant because we're differentiating partially. So we would have, first, because of the power rule, twice the logarithm of alpha cosine x, and then because of the chain rule, differentiating this logarithm gives us alpha times cosine x down there in the denominator. And of course, we have to differentiate this thing again because of the chain rule. So we get this constant multiple of cosine x, which cancels out quite nicely. And this implies that the derivative of I with respect to alpha equals 2 divided by alpha times the integral from 0 to pi by 2 of the logarithm of alpha cosine x divided by x squared plus log squared alpha cosine x dx. Now, I admit that this new integrand doesn't really look all that good. It's just as bad, if not worse, than the integrand we started off with. But here's a hint. Whenever you have this kind of structure where you see a sum of squares in the denominator, and you see one of those terms in the linear power that is up in the numerator, then that's a signal to apply a Laplace transform or reference a Laplace transform of a sine or a cosine function. In our case, we recall that the integral from 0 to infinity of e to the negative st times cosine of a times t dt equals s divided by s squared plus a squared. So in our case, all we have is s equal to, I'm actually going to introduce a couple of negative signs here. And this is something I added in hindsight while writing up the solution for this integral, before making the video. So yeah, these negative signs actually helped. So if I let s here equal negative log alpha cosine x, and I let a here equal to x, then that's pretty much all I need. And using this knowledge, I can write the integral as a double integral now. And this is actually something pretty useful. I wasn't a huge fan of this trick, using multivariable calculus to solve integrals, specifically using double integrals, that is, to solve integrals. But I've grown quite fond of it. So in this case, we have negative 2 by alpha times the integral from 0 to pi by 2 of now the integral from 0 to infinity of e to the, what exactly do we have? E to the t times the logarithm of alpha cosine x times the cosine of tx dt dx. Okay, cool. Now, what exactly is this exponential term over here? This exponential term should sort out to a to the t times cosine to the t of x. So we have negative 2 by alpha times the integral from 0 to pi by 2 of the integral from 0 to infinity of a to the t times cosine to the t of x. No, wait, this was alpha. Terribly sorry about that. The parameter is alpha. So alpha to the t times cosine to the t of x. Why do I keep writing dx today? Times cosine tx dt dx. We now switch up the order of the integration operators, and that means we have negative 2 by alpha times the integral from 0 to infinity, integral 0 to pi by 2, alpha to the t, cosine to the t of x, times cosine tx dx dt. Notice now that the first term is independent of the x variable with respect to which we're integrating. So we might as well take it outside the first integration operator, and we have negative 2 by alpha times the integral from 0 to infinity of alpha to the t times the integral from 0 to pi by 2 of cosine to the t of x times cosine of t times x dx dt. Now I'm going to make use of a very nice integral formula that I'm not going to prove here. I'll make a separate video proving it, or a write-up for my Instagram. And that formula is the integral from 0 to pi by 2 of cosine raised to the n of x times cosine of n times x. And of course, this is more general with n and m being different, and that's a lot cooler, but for our purpose, this is fine. I'm just going to write out the case for n and m being equal. So we have pi divided by 2 to the n plus 1 times n plus 1 times the beta function evaluated at n plus 1 and 1. Now, all we need is n equal to t, and we just need to figure out what this beta function looks like. So for the case of n being equal to t, we have beta t plus 1 and 1. So let's expand this in terms of the gamma function. We have gamma t plus 1 times gamma 1 divided by gamma at the sum of these two arguments, which is t plus 2. And of course, this can be written again as t plus 1 because we can make use of the recursion formula for the gamma function. Gamma 1 is just 0 factorial, or 1. So we have gamma t plus 1 divided by t plus 1 times gamma t plus 1, and some cancellation taking place, meaning that we have 1 by t plus 1. Okay, cool. That's what our gamma function looks like. The beta function, that is. And let me just zoom out a little bit and just decrease the font size and just take it over here. Yeah, still perfectly visible. And lock again. So all of this implies that the derivative of I with respect to alpha does indeed equal just one moment. Much better. So the derivative of I with respect to alpha equals negative 2 by alpha times the integral from 0 to infinity of alpha to the t times the result of this integral, which is, in our case, pi divided by 2 to the t plus 1 times t plus 1 times 1 by t plus 1 dt. And we see some nice cancellation taking place. And we have a very simple integral to evaluate. It's negative 2 by alpha times the integral from 0 to infinity of, I'm going to take a factor of 2 outside, so we have them canceling out, and now I have pi outside, alpha divided by 2 to the t dt. Now, a recurring theme in my videos on using the Leibniz rule to evaluate integrals is that I prefer not to state the domain of the parameter at the beginning of the solution development. And the reason for that is I like to keep it flexible. I like to just continue with my solution development, and once I hit a wall or the requirement arises, I will then define the alpha parameter in a strict manner, in a strict sense anyway. So in this case, we do know that the target case is alpha equal to 1. That's the target case. And right now we have indeed hit a wall because we have alpha by 2 raised to the t, where t here is tending to infinity. So I would like if alpha is less than 2. So let's state the domain of the alpha parameter to be this open interval between 0 and 2. That way, we see that alpha by 2 is less than 1, so alpha by 2 to the t tends to 0 as t tends to infinity. Okay, cool. That is quite convenient. So this implies that I prime of alpha equals negative pi by alpha times minus in the limit as t goes to 0, we have a 1 up top times the logarithm of alpha by 2. Okay, this is quite nice. And let me write this as, I could cancel out the negative signs, but I might as well write this as pi divided by alpha times log 2 minus log alpha. Why do I need those parentheses? Log 2 minus log alpha with a negative sign up top. And the reason for that is I'm going to have to introduce another logarithm later, as you can see. And come to think of it, those extra negative signs I added in the beginning, I don't think they were necessary. Why did I add them initially? Where did I mess up? I probably messed something up, or I missed something while writing out the solution development. Anyway, it's cool. Comment down below if those were even necessary. I believe they were not at all. Anyway, so we have this structure for the derivative of I with respect to alpha. And now that we have the derivative completely in terms of the alpha parameter, we'll integrate this with respect to the parameter to recover back the integral function. So we have I of alpha, and this here equals negative pi times, we have this function in the denominator, and if you differentiate this with respect to alpha, we get negative 1 by alpha, correct? So that means we do have a structure where we have the derivative of a function. We have a function in the denominator, and we could write this as negative pi by alpha. It means the same thing. So we have a function in the denominator and its derivative in the numerator. So we just apply another logarithm. So that means this negative sign gets absorbed into the derivative thing. And we have the logarithm of the logarithm. Much better. We have the logarithm of the logarithm of 2 by alpha. And now you see why I wanted to write this as 2 by alpha. If I write this as alpha by 2, then this thing is less than 1. Then the logarithm here would be less than 0. Then I would have a complex logarithm. Anyway, so this is the structure, but we also have a constant of integration c, which we now have to figure out what it equals. I've expanded the integral function on the left-hand side to give you guys a better visual of what's going on. The thing is, we need the constant of integration. We desperately need the constant of integration. But for that, we need some initial value or particular value of the integral function, that is, the value of the integral function at some value of alpha. Problem is, these logarithms make things incredibly complicated. So even if you think of something simple like letting alpha equal to 0, or in our case, letting alpha approach 0 from the right-hand side, these logarithms don't allow for that because we know that the logarithms would blow up. But there's a way to work around this problem. I'm about to do something incredibly strange. Why on earth am I about to do something incredibly strange? Or what was the need? What brought about the necessity for such line of thought? Well, here's the deal. I'm incredibly stubborn. It's quite useful at times. Try it yourself. Try spending 2 days fixating about an integral, trying out different places for the parameter. There aren't really many places you can insert the parameter. It could be over here as a coefficient, or it could be a coefficient of the entire thing. Yeah, not exactly very fruitful efforts. But then you come back to this point, and then you're like stuck, and you're fixated, and you're too stubborn to give up or try something different. You should try something different at that point. But if you're incredibly stubborn like myself, you'll ask yourself, what do I want here? What would make my life so much easier? In our case, having another function in the denominator of this argument. Another function should be a logarithmic function because we have one of those in the numerator, and the limits of logarithms over logarithms are quite easy to work out, even intuitively. Even if you don't want to apply L'Hopital's rule, you can work them out intuitively anyway. You've had so much experience of working with limits by this point. So that's what I wanted. And so it struck me like a lightning bolt that why not add the negative of the integral from 0 to pi by 2, now hear me out, of the logarithm squared, terribly sorry about that, of alpha dx. Now log squared alpha is a constant in the x realm, so that means this integral sorts out to negative pi by 2 log squared alpha. Okay, cool. Now, how exactly does this benefit me? Well, this thing would benefit the left-hand side and this thing the right-hand side, especially if I introduce a factor of 1/2 over here, and to balance that I have to multiply by 2, but using the properties of the logarithm, that means I can write this as an exponent of the argument, and the cool way of writing this is log squared. And that means I can factor out a pi by 2 on the right-hand side as well. Anyway, on doing this acrobatic little stunt for evaluating our integral, on the left-hand side, we have the integral from 0 to pi by 2 of the logarithm of what exactly? Using the properties of the logarithm, I combine these two into a single logarithm of x squared plus log squared alpha cosine x divided by log squared alpha dx, and on the right-hand side, pi by 2 factored out, we have the logarithm, again using the properties of the logarithm, of log squared 2 by alpha divided by log squared alpha plus the constant of integration. So by luck and sheer stubbornness, there's a ray of light. What I'm going to do here is take the limit as alpha tends to 0 from the right of both these arguments of the logarithms. What happens over here? Well, the limit, terribly sorry about that. Again, terribly sorry about that. The limit as alpha tends to 0 from the right of x squared plus log squared alpha cosine x divided by log squared alpha can be worked out using an application of L'Hopital's rule or two. So that's the limit as alpha tends to 0 from the right. Differentiating with respect to alpha, upstairs and downstairs, gives us 2 log alpha cosine x and the need for some writing space. So we have alpha cosine x, and then we need the reciprocal of the argument, then the derivative of the argument. With respect to alpha, once again, some nice cancellation. Okay, cool. And in the denominator, we have 2 times log alpha times 1 by alpha. And again, we have some lovely cancellation taking place. So you could apply L'Hopital's rule again, but it's actually pretty easy to see, especially when you've solved so many calculus problems at this point, which I expect you've done because, well, I've done over 300 videos now, and I'm pretty sure that the only people who watch my videos regularly, at least, are calculus nuts anyway. So the logarithm of a linear function in alpha divided by the logarithm of another linear function in alpha, that would be approaching 1 as alpha tends to 0. Again, you can verify this by L'Hopital's rule if you want. And it's exactly the same thing on the right-hand side, especially if you write this as alpha by 2, which is completely valid because of the squared cancels out the negative sign anyway, making things incredibly clear. So both of these guys approach 1 as alpha tends to 0 from the right. That means you have log 1s on both sides of the equation. And we know what log 1 is, right? That's 0. So that means we have 0 equal to 0 plus c, which implies that c equals 0. And I'm pretty sure you guys are quite happy to see that, just as I was. Wow. So finally, all we need is the target case, that is alpha equal to 1. We know in general for the integral function I of alpha, we had log 2 by alpha plus the constant of integration c, which is thankfully 0. This implies that the target integral here equals log, wait, we had a factor of pi as well. So it's pi times log 2, which is pretty damn cute, to be honest. I mean, I'm quite surprised that such a monstrous integral of log trig functions with squares in the argument results in something so adorable. And wow, that was one roller coaster of a solution development. And this whole journey is one of the many reasons I enjoy applying Feynman's trick. I really love applying this technique. I hope you enjoyed the video. I hope you learned something. Be sure to like and subscribe. Do drop me a follow on Instagram as well. And in case you like the channel, you want to support the content I'm putting out, you feel like I'm doing a good job teaching people or whatever, then consider supporting me on Patreon. All links in the description box. Thank you. See you next time.